a couple different ways you can do it. You can have Panoply open for two different simulations that you've done, okay, where you're interested in the difference between one and the other, and then you can open the same file like surface temperature for two different simulations, and then you click combine plot, and it gives you the chance to combine the two plots, and you can then choose from a menu that lets you take differences or fractional differences or ratios or sums or things like that, and for things like vector quantities, like wind quantities. If you give it two different directions, U and V, you can make a vector plot out of it.
Sure. So create plot, and the next one would be
so create.
Yeah. The vsurf would be combined plot,
and then open the vsurf. Plug it down. Vsurf, V component of surface air wind.
No, don't cancel. But combine plot.
Sorry?
But combine plot this time. Don't double click it.
Don't double click this?
Yeah. Go up to combine plot.
Yes, boss. Combine plot.
Yeah. And then let's T-surf.
So go select U-surf on the menu.
Yep. So now you're combining that, and I hit combine. And so that's the wind field. You can make this all white, and it's better to do vectors with this. So you can you can do. We'll go to the array there, array 1 minus array 2.
Yep.
And then go down to vector magnitude.
Yep.
And so then you could generate a vector, and then you could white out the color map, so you just see the arrows, and then play with the arrow lengths and all that.
So you can see the values.
So that's your wind field.
That's your wind field, yeah. So go to scale, and then set this to white.
Yeah, you just have to choose the uppermost color bar, which is white.
The one thing you can't do in
There's a lot of color bars.
The one thing you can't do in Panoply is three things. So you can't plot the wind field over, say, like sea level pressure or something. You have to be more fancy with that.
Right. So here's a vector plot. This is one of the more sophisticated things I think that they can do. Yes, sir.
Looking through the data fields in the multimedia file, they all seem to be 2D, very lat long. I was wondering, how would I make just vertical profile plots and temperature and water vapors? It's not, unless I'm missing them in the data set.
So
that's not AAJ. That's
it's AI. So if you want, can you open an AIJL file?
I have an AIJK.
AIJK is fine.
Okay. Up here.
So AIJK has.
AIJK file.
So look at TB, for example.
TB, temperature. Yeah,
something similar. Okay, and so okay, that was the 2D file, but now go back again. Don't be so quick to make the plot.
Yes, boss.
Okay, just click. Okay, now click the bottom button, and say change from horizontal to vertical. Okay, and along the PLM axis.
PLM is pressure on
Layer pressures.
layer pressure.
Okay.
Is this plot with a lot of information?
Okay, so yeah, what?
Oh, this is.
But you're right, yeah.
Usually this works.
Well, I don't know.
Oh, this might be the partial file. Sometimes doesn't have
Oh, the partial
all
file doesn't
fields.
have that. Okay.
So it's only the first time step. So sometimes it needs a bit more running time.
All right.
This
Well,
should usually
but if
work.
anyone wants to see, I can show offline with
No,
run
it's
that
not there.
animation.
No, it's not there.
I guess my question is also when I'm doing scale ACC, so it's
Yep.
doing scale ACC, AIJK, I can do AIJKL.
No,
AIJK
So-
or AIJL, they're two different.
Okay, so
Okay.
there's all different combinations, but
Yeah.
but the simplest thing you can do if you don't mind all the files is just do scale ACC all,
Okay.
and then you get
And I get everything.
that complete list of diagnostic files that Mike had up
Okay, that's.
before the
In all
break.
three-dimensional.
You might not want all of them, and if you don't. And if you don't want all of them, then you have to pick the specific one you want. So the 3D atmospheric files are AIJK and AIJL.
Okay.
the K ones tend to have more general circulation stuff in them. The L ones tend to have more thermodynamic stuff in them.
I was mostly being.
I'm
I was
looking for a
mostly being.
tightly locked world, Proxima Centauri, that we've done in a recent paper.
So we're in the process of trying to document all of these diagnostics files, and hopefully we'll have plans to maybe eventually send that out to everybody. We started it. It's just
I put
a
the
long.
links.
It's a long process.
I put the links in the PowerPoint slides.
To the ones that
the
we
ones
have
that we
anyway.
filled out so far.
Yeah, yeah.
Here's an AIJ. Or
So Eric, see,
no, this is an AJ.
there's a lot of them, so the scale ACC will take a long time. If you know which particular ones you want, though, it's a much more concise
Mhm.
process. That's why I'm shaking my head, because it's a lot of files and it takes a long time to get all of the diagnostic files.
For what runs?
Well, the ones with tracers, definitely.
Oh, well, the runs with traces. Traces are always the problem in the GCM. Everything is easy in the GCM if we didn't have tracers, right?
I also have a
That's
Python
probably
script.
true.
If
But
you
for
have,
a run that you don't have tracers in, I mean, while we were sitting here before, I just created an ACC all file myself.
Okay.
And it takes like a couple of seconds to get all of them, if you want them. But yeah, but you turn on tracers and things slow down a
Things
lot.
slow down.
Yeah, yeah.
Let's try.
Also, if you have like 1,000 years, so you have 12,000 ACC files, and you want to get AIJ from all of them, I have a Python
But
script
that wasn't
that just
full.
scale ACCs every
Oh,
I didn't realize that the
I have
non-tracer
this
ACC files were quicker than that.
Oh yeah, yeah. Well, right, so you got right. You got a tracer for every constituent, right?
Yeah.
And
And
Okay.
there's like how many?
So I thought I would just quickly show this is a 100-year average of a Proxima Centauri B run that's in our
Oh yeah, yeah.
recent
Yes,
Del
that's-
Genio et al. Paper that should be impressed now. I
What?
guess. This is a 100-year average of the last from a 4,000-year Proxima Centauri B run that we have
it's
in
not
our
impressed yet. We're
most
waiting to hear
recent
from
paper
Master
from Del
Biology.
Genio et al. We just submitted the last referee report request. And here you can see, again, a 100-year average. It's a tidal locked world. This is the incident shortwave at the top of the atmosphere, and it is over the date line where it should be. So, a nice sanity check to see. Now, again, it looks kind of funny being here, but you can change where it displays. If I want to change the center latitude to 180, then it looks a little bit nicer. You can see where the center actually is, or the date line, etc., etc. I can turn off the interpolation if I want. Things of this nature. I can click here, and I'm getting around 880 at the center, and we actually used 881 watts per meter squared from Bootley et al. For the simulation. So the value is actually surprisingly close to what it should be. Gives you some.
Can you just switch to the map to vertical perspective?
Vertical.
Go to the map tab
Yes.
and select vertical perspective instead of equirectangular.
Vertical. Sorry.
Yes.
I don't know what vertical is.
Under projection.
Just open
Under
just open the
projection.
menu. Yeah, yeah.
Oh, you want vertical here?
Vertical perspective. Yeah.
Sorry, let's take a look. See, we work together.
Okay,
all the
there it
time, and
is,
We
yeah.
still don't speak the same language.
Okay. And switch the latitude to say 30 or something like that.
Yeah, this is cool.
So you can, so if you're doing something for public
Consumption.
relations purposes where people are used to seeing an actual planet instead of some map of things that they're not used to, vertical perspective can allow you to do that. And you can get artsy and look down on whatever latitude you want or whatever longitude you want. You can also look at it from close up or far away if you're interested to, if you plot the center, if you change the center distance and so on. So that's kind of nice if you're just doing some PR thing or an educational thing or whatever. It's nice to use that.
Again, if you want the value in a given grid cell, hold the Option key or Alt key down, depending on what kind of computer you're using, and just click, and you'll get the value for that particular grid cell.
And also, if you click the Array tab in the upper left, you're seeing the entire array of things. No, the upper left.
Oh, sorry, upper left.
Then there's all the numbers that are actually
There's
getting
actually a
plotted.
table.
which you can download as a file if you want.
Yeah. So Monopoly has, as you've seen here, this is a very, very small fraction of the number of features it has. There's a tremendous number of diagnostic variables you can look at. We have been creating these for 40 years. We probably have created every one that we could think of within this building, but if there's something you need and we don't have it, we can probably create it, or there's a way to generate it from what we already have. Okay, so was everybody able to open this thing up in Monopoly and play around with it and get a feel for these things? Remember that scale ACC command generates any of these variables that you're interested in. Right here. Any of these things. So it's always the same. Scale ACC, the name of the file that you're interested in generating the diagnostic for, and the name of the diagnostic you want to generate, whether that's AIJ or AJ or AJL or any of these others that we've showed you in these things. And again,
Or all.
Sorry?
Or all.
Or all, yeah. If
As
you
long
type
as- as long as you don't have
file
traces
name
turned
all,
on.
every single one of these diagnostic files you're interested in.
I just timed it. And
No
it took
problem.
literally as long to make the TAIJ file as it did to make everything else.
Tracers
So
files are very data intensive.
they're prodigious.
So there's a reason why the ACC files are fairly large. Sorry, I want to show the size of one of these. 55.8 megabytes is the size of the ACC file, or the AIJ file, sorry. Oh no, this one's, 5 megabytes, 5.5
5 megabytes, yeah.
So the
Now that's-
ACC files are...
That's for the 4x5 model. Start
Yeah.
running your model at higher resolution
And that's a 2D file.
and that's a 2D file,
That's
right?
a
So,
2D field. I think I have...
3D field.
so
let me see. I
like
think I
for
have
the
some
for the
of
Earth
these.
model that we typically run at 2 by 2.5 degree resolution, the AIJ file is more like 20 something megabytes.
I'm just trying to find an ACC file so I can show you how big they actually are.
While you're looking for that, can I just say that in the
Speak loudly.
we talked about this recently, so I bring it up. In the run deck, there's a parameter called cloud rad force. It's cloud radiator forcing, and basically, when that's 1, the radiation is called twice in a model, and so it calculates all sky and clear sky radiator fluxes. So you'll see diagnostics like shortwave cloud radiator forcing, which is calculated with 2 calculations, one in which clouds are transparent to radiation and one in which clouds see the radiation. And just a trick you can speed up your simulation by setting that to 0, and so you don't get those diagnostics, and then you can turn it on in the last like 5 years or whatever of your simulation in order to save those quantities if you want to. But you can run a simulation a lot quicker if you turn that off during most of the simulation. You lose some of those diagnostics, but then you can turn it back on in the last 30 years of your simulation or something.
Yeah, this particular partial file, your ACC file, is 48 megabytes. Should be around that for all of you. So the ACC file is that size for a reason. There's a lot of stuff in there that can be generated by using the scale ACC. Okay, any other questions or any questions about these post-processing diagnostic files that you're interested in asking us about? If not, we can move on to, before lunch, discussing quickly these equilibrium. How do I know when the model is done running? It's not that I just turn the model on, run it 10 years, and say, write my publication. It's not so simple, unfortunately. And I have gotten that question in talks. How do we define when the model's in equilibrium? And even by non-GCM people, Jack Lissauer at NASA Ames asked me once if we were running the model to equilibrium. And I had to explain in some detail how.
It's a good question.
It's a good question, yeah. Because maybe you don't know better and you didn't do it. And then you would say, what's equal, what, huh?
A very Jack question.
Yeah, very Jack question. I know Jack very well. He was my neighbor at Ames
So if you're, so you were showing us the other day, or yesterday, the CO2 file is constantly changing. As
It can change for
so
Earth runs if you want it
So
to.
what does that mean to become an equilibrium? Constantly changing, essentially.
Well, then if you run it forever with changing CO2, then it won't.
That's right. If you keep running it forever, as Chris is saying, it won't. You keep forcing it. You're forcing the model, forcing it, so it won't.
So a lot of the experiments I think we all have in mind are experiments where we do.
Oh, you do? Oh, a lot of you have in mind to do experiments where you're forcing the model continually?
I do.
Why would
I
you
mean,
do
with the
that?
secular trend in something?
Yeah, with trends and parameters over the years.
Well, then it
No?
shouldn't come.
Yeah,
to
then it should
equilibrium.
not come into equilibrium.
But remember, timescales are limited here. You can't run more than
But
maybe 10,000
but how
years.
far from equilibrium it is depends on things like, well, you know, what kind of let's say if you have a 10 bar atmosphere versus a 100 millibar atmosphere, then you'll be farther from equilibrium at any given time in the 10 bar atmosphere. Likewise, you put a big thick ocean underneath you, and you'll be farther from equilibrium at any time than if you have a very thin ocean underneath you. So that's like one of the big things about Earth climate change, right? Is that we're increasing CO2 now, but even if we somehow magically turned off all the CO2 emissions today, the globe would continue to warm up for decades or centuries because it hasn't quite equilibrated to all the stuff that's already in the system, right? So that's what you'll get if you're actually secularly increasing CO2 or any other quantity. Yeah.
Constant concentration, not zero emission.
Yeah.
Basically, when you're doing run, it's nice to at least get equilibrium to some kind of benchmark state. So what we are, for example, doing for Earth, we can see that the benchmark is pre-industrial climate. So we run our model to equilibrium for pre-industrial climate, and then we assume afterwards the model is not at equilibrium. So we drive it with certain forcings, and so we don't expect equilibrium anymore. But we know that at least the state we started with was in equilibrium, so we didn't have anything funny there. Ocean, like a bit of heat that released over centuries. I don't know what you would do for exoplanet. Invent something like that. What would be imaginary equilibrium before you start forcing something?
Okay, so I thought...
We going to talk about equilibrium?
That's what I'm doing right
Oh,
now,
okay.
boss.
Because it's pretty
Highlight
complicated.
it.
It's actually pretty complicated.
It's complicated and important. So
Yeah.
I thought I would show a typical plot that we use in-house to decide if a particular model is in equilibrium or not. So this plot I'm going to show you is generated from the diagnostic files we have just discussed. In particular, all of the variables you're going to see in this plot are generated from the AIJ file. What we do typically is we generate every monthly AIJ file from the model run, and we look at quantities within there of interest for whatever kind of quantity we're interested in seeing if the model's in equilibrium. And there's a couple of different ones that we're interested in. So for this particular run, just give you a little background on it, it's receiving about 70% more insolation than the Earth is. It's a fairly slow rotator. It's got 120 days linear rate, and it's using what's most importantly a Q flux. What we call a Q flux equals zero ocean. So this ocean has no heat transport. It's what is known as a slab ocean, or a mixed layer ocean, or a thermodynamic ocean. No ocean heat transport horizontal takes place, only communicating with the atmosphere. What's nice about these? They come into equilibrium very fast in terms of the radiative balance in the atmosphere. That's why people like them. If you don't have a lot of CPU cycles, you run these slab oceans, and that's what most of the exoplanet community has done in most publications up to this date. I think ourselves are one of the few groups who have consistently run fully coupled oceans, but they can take thousands of years to come into equilibrium. And I'll show you an example of that as well. So this is just an example of what one of these diagnostic plots looks like. So there is a variable in the AIJ file called net_rad_planet, and that's the net radiation for the planet that it sees, that the model sees basically. And so what I've done here is I have plotted that value for the 200 years, every month. I've extracted that value for every month, and I'm plotting it for the mean, or for the global mean value for that quantity. And then I plot that up, and then what I've done here, first of all, that dotted line I put at 0, because that's where I want it to be. I want the mean to be at 0, and the value I put there, in this case, I'm not sure that is correct, it should be 10 years, is the mean value of the net underscore rad underscore planet for this run, for the last 10 years, the mean value of the global quantity. And you can see here, it's 0.06 watts per meter squared. It's much less than 1. It's actually less than 0.2, and that's the bar we tend to set within this building. The value of net rad planet averaged over the last 10 years for a world like this should be less than 0.2 or greater than minus 0.2. And you can see in this case it is. And it came into balance pretty quickly, if you see. It actually probably came into balance in the first 50 years of the run. You probably want to ask why I'm going to 200 years. I'll show you that in another plot. Tony, do you want to add anything else to what I've just said?
Well, so that 0.2 is kind of arbitrary. You say, you know, ideally I'd like it to be actually 0, right? But you know, 0.2 is pretty close. Sometimes with these more exotic planets, we don't quite reach that. I think we've had a few runs where we couldn't get it down below 0.5, and if you actually look at Earth climate models, it's sort of amazing. If you look at the entire universe of Earth climate models, that there are some models that don't get that close to 0 for their. So net radiation is just absorbed sunlight versus emitted heat, right? It's the equation S0 times 1 minus A over 4D squared equals sigma T e to the 4th. It's the two sides of that equation. So in balance, it should be 0 if you're not increasing CO2, right? Yeah. So it should be 0. It never gets all the way down to 0. We try to do, I say we, I had nothing to do with it, but the people who developed this model tried to do a very good job of actually conserving things like heat and mass and water vapor and stuff like that, and it's sort of partly a measure of how well you're doing on those things. But they're always little niggling things, like I think we have suspicions maybe about the lakes or something like that, that they're not quite as conservative or whatever as they need to be. So you don't get all the way down to 0, but we do a pretty good job. Some of the models that are climate models that are used for like IPCC don't get to within 1 watt per square meter of equilibrium, which is kind of amazing, which is saying they're not paying as close attention to conserving things as they need to. But we generally consider a small fraction of a watt per square meter to be pretty good. And just occasionally we have a weird planet that doesn't get there for whatever reason that we haven't figured out yet.
I aim for plus or minus 0.2, basically. If we can get there, generally we feel pretty good about it. In this case, you can see it's much less than that even. I also plot up a couple other things to make sanity checks. T-surf, surface temperature. So that T-surf value from the AIJ file. Here I've again plotted every month, and you can see it's extremely flat after only 20 years, basically. That gives me a good feeling inside that things are going in the right direction. Albedo, I plot that up as well. The albedo, I hope, should be more or less the same. Shouldn't be changing a lot. There shouldn't be a lot of changes in any of these quantities once the model has come into equilibrium. I won't talk about the next quantity, I don't, unless Tony wants to, but you can see here.
What is it?
That's this net cloud radiative forcing quantity that we generate, but which we need for other purposes, but I won't go into that. I plot up here, ocean ice fraction. I showed you that also in the AIJ file. You can see here it's 0 because this planet is given 70% more solar insolation than Earth does, so there's not a lot of ocean ice in this model. But if you go to lower installations, which we do for some of these totally locked worlds, it's a quantity to keep an eye on. And that's why I plot it every time. This is just the default MATLAB script I use to pull quantities out and plot them. It's a good idea to keep an eye on it, because sometimes it can start going very large and you want to know why it's going very large. Maybe it just keeps on going. Maybe there's a bug in the model. Maybe you're getting close to the ocean freezing at the bottom. These are things you want to keep an eye on to make sure that you're where you expect to be in the model. That's why I plot up all of these. Let me show you another some more for this particular run. This was another set of diagnostics that I typically plot up. Most of them are not going to be of interest because it's a very hot run. But again, ocean ice fraction of nothing. And there's something here called G ice. So that's how much ground ice, how much ice is in the ground layers of the model. All the layers. There's 6 layers in the ground hydrology model. And here you can see it's 0. Well, because the planet's extremely hot. Not a surprise. ZSI is the amount of lake or ocean ice in the model, basically. Here, this value should be 0. It's just undefined in this case. Snow deposition rates. There have been problems in again, cold runs with snow building up to large values in individual grid cells because Model E, one of its many failings, is that it does not have interactive land ice model. We don't have, glaciers cannot move in this model basically. So if you get a lot of snow deposition at a high latitude for some reason, it can build up to thousands and thousands of meters. We have a way to limit that. It's not physical. We can say you can't build more than 100 meters, otherwise dump it into those iceberg arrays I talked about yesterday, the GL melt. But again, it's something I keep an eye on.
But model failings aside, there's real physics of the climate system going on here too. So the types of runs in which you're not going to get into trouble so much with the water balance are runs where every grid box on the planet sees the sun part of the time. So if you do the actual Earth with obliquity, then although it gets very cold in the winter, things warm up in the summer, and then the snow melts, and so on and so forth. And while you can have issues over Antarctica and Greenland, otherwise you don't have too much of a problem. But I think the run that Mike is showing you is a run where he zeroed out the obliquity and eccentricity, and so beyond some latitude, you're in night all the time. Likewise, if you do a synchronously rotating planet and you've got land on the night side of the planet, then in either case like that, if you've got land anywhere that never sees the sunlight or starlight, then water is going to migrate toward that land mass, fall onto it as snow, and just keep on piling up there because there is no mechanism for the snow to get off the land once it gets there. If we had a land ice module, then you could form glaciers and you'd be calving icebergs and dumping stuff into the ocean, and you might eventually come into balance. But even if you had that, though, that is a fundamentally long timescale process on the real Earth, okay, that takes thousands of years or tens of thousands of years or something like that, to occur, and you really shouldn't come into equilibrium quickly for stuff like that. And there have been people who've written papers about this for exoplanets. There's a paper by Jun Yang and Dorian Abbott a few years ago where they actually tried to take the NCAR model with a synchronously rotating planet with a continent on the night side, and then do an offline calculation with an offline land ice dynamics model to try to figure out in equilibrium how thick the ice on the night side would get and how much of the ocean would be lost and so on and so forth. So it's there's real physical issues here rather than just a limitation of the model.
Yeah, but I should mention that even if
Tony?
Go ahead.
There is a comment on the chat window that is probably the answer is going to be too long, but if you want to comment something about it.
Oh, there's real internal variability.
I think there is a suspicion out there that every climate model on the planet does not have enough internal variability. I don't know that anybody can prove that, but as a general rule, climate models tend to have El Niños that are too sluggish. They have difficulty making observed tropical phenomena like the Madden-Julian oscillation, things of that sort. This particular generation of the GCM, I would say, has those problems. We're looking forward to the next couple of generations of the Earth model, which have much better climate variability. In fact, the latest that we've seen is that maybe the model has even too strong an El Nino in the next generation of the model. And so I think Planet 2.0's variability will look somewhat different and overall somewhat better than Planet 1.0.
There is internal variability, so don't just look at 1 month standard.
Yeah, there's internal variability. Never look at just 1 month. That's right. Well, as you can see here, and this is plotting every month for 200 years.
By the way, it wasn't brought up, but there's a variable in the AIJ file called AXYP. That's the grid cell area, which it's approximately cosine latitude. But when you're making these global means, you need to weight your variables by that variable. AXYP is, yes, you should be using a lot.
Maybe just another thing to mention, though, as far as variability goes, and that is that there have been questions raised in the literature for exoplanets about possible bistability of certain types of climate systems, and that is, yeah. So you work with Adrian, so Adrian thinks about that from a couple of climate tectonic system. We don't do that part of it ourselves. But even just within the climate part of the system itself, there's the possibility that you might get bistable behavior, and you can get sometimes longer-term transitions between regimes when you're heading to equilibrium, especially on a planet that is cold enough for part of the planet to be covered by sea ice. Those tend to be the more interesting things. If you look in the literature, planets with sea ice can sometimes go between two different states. Most of the time our runs will look fairly well behaved, like this run that Mike is showing you, where you're kind of confident everything is okay, but every once in a while we do something where we get the impression that the run might be sort of on the boundary between two different dynamical states, and you'll see fluctuations on timescales of a few years that seem to be larger, and there's no long-term trend, but we think those are probably real things where the model might be at a boundary between two different climate states. And then every once in a while you'll see a situation where it just takes the ocean a long time to respond, and you'll run for centuries, think you're in equilibrium, and then all of a sudden it'll switch over into another state as the ocean is finally deciding it wants to come into balance. And so depending on the runs you're doing, you might want to experiment a little bit with that. You might want to try starting your model from a warm initial condition and a cold initial condition to see whether you wind up in different places in the end, and so on. We have not yet, I think, identified any true bistable behavior in terms of sensitivity to initial conditions in this model, but that does not mean that it does not exist.
I have, it does exist.
It does? Okay.
Okay.
Yes. Although I found, let's say I have a planet and a cold star and a warm star, there's certain combinations of orbital of solar CO2 forcing where one ends up mostly ice-free and one's a snowball, and I found that transition can happen in a couple hundred years, and so if you plot the surface temperature after year 200 or year 500 or year 1000, you've already found it. So I'll show that.
So this is the same kind of plot I just showed before with much less solar insolation forcing, so just 10% more, and you can see the values are quite different. Ocean ice fraction actually has now got a value, a mean value, G ice, so the amount of ice in the ground has gone up. You can see it's stable. So this makes me feel good that things are pretty good, except for the last quantity, mass of the water in lakes. So this is telling me that is not come into equilibrium yet. So there's still water volumes being transported around trying to come into equilibrium in this model. So if I show you the first version of this plot, you can see that radiatively I'm at 0.02 watts per meter squared for a 10-year average. It looks very good. So the radiative balance is good, but it looks like my water hydrology cycle is not quite in equilibrium, even for this Q-flux ocean. So I probably should run this a little longer if I'm concerned about diagnostics related to ground hydrology. Okay? If I'm not worried about that, I'm only interested in atmospheric dynamics, like a global average surface temperature, no worries. This is not that important. It's not going to change those values by anything significant. But if I am interested in ground hydrology diagnostics, I have to be a little careful about this run and make sure that it's in a stable state. Okay.
Just give you an example of that in the literature. Robin Wordsworth and colleagues published a paper a couple of years ago about ancient Mars, and they specifically were trying to answer the question, you know, with the right combination of greenhouse gases and Robin's new radiation for collisionally induced absorption. Could you get a climate that would explain the locations of the valley networks and so on and so forth. Anyway, the bottom line is they started that model with, I think, like a certain amount of water in the soil, and then they waited for that water to migrate to the places where on the planet where it wanted to migrate to, but they didn't have time to actually wait for that to happen because it takes a long time to do. So what they did was, like, they ran the model for 2 years and calculated sort of de-snow de-time, and then they took that de-snow de-time and extrapolated it into the future for 100 years, and then ran the full model again for another 2 years, and then ran this then extrapolated again for 100 years, and they did this a bunch of times, and then they eventually made the extrapolation smaller until they finally came into some sort of equilibrium so that they could kind of predict where the snow would accumulate and where it would not accumulate. So that's the type of game you have to play with these models if you're doing something that requires that you pay close attention to what the water cycle is doing.
Yeah, so I thought...
Actually, I just wanted to add, like, to this snow depth, Tony started to talk about. You accumulate snow not only on tidal planets, like on the night side, but even for, like, normally rotating planet, if you have very low obliquity, if it's sufficiently cold, then you start to accumulate snow on the poles. And if, for example, you have land planet, no ocean transport, then basically you would accumulate it indefinitely. It will be a very long process, and for example, yes, if you look, it will look like close to equilibrium, but if you look at ground hydrology diagnostics, you will see that we are slowly depleting water everywhere, and eventually it's getting frozen like at the poles. So it may take like thousands of years, but eventually you will freeze all the water. And I guess that's what people were doing with this Mars experiment, that they didn't want to run more than thousands of years. But eventually, yeah, you get, I would say, reporting final state.
So here's another example. This is for the fully coupled ocean. If you look at the x-axis here, you see that it's run 1,700 years. You can see that after 200 years, I'm probably not in equilibrium in a lot of these quantities. But you can, and actually I was not in the net red balance. You can't see it here, but basically it was going down. It took a long time to come into balance net relatively, but here you can see I'm now below my plus or minus 0.2. But of course, in this model, I'm really concerned about the ground hydrology. Let's look at those numbers. And here you can see that here I have made sure that MWL is finally looking fairly flat at the bottom. This is getting a lot of insulation. This is 40% more insulation. So I just wanted to show you a long run. Let me show you one that's a little bit less crazy than that.
Mike, have you checked if the statistics works for 20 or 30 year average? Or is the 10-year
The
window
statistics
fine?
work for any average. What do you mean?
Well, I meant,
Yeah.
is the 10-year window, so, you know, do you get,
Is there something
does it
physical
change
that-
if you go to 20 years versus 30 years? Or if you take a 10-year average versus a 20-year average or a 30-year average, does that number appreciably change, or is it
Why it's
stable?
Well, that's what we have used for the Earth model, basically, typically, is a 10-year average. I don't know why we particularly
Is there a
chose that
physical
value.
reason for that?
On Earth, I'd say the physical reason is that most of the variability in the Earth, most of the natural variability in the Earth system, but not all of it, is smoothed out over 10 years. However, the ocean has decadal variability in it too, and so you'll see that decadal variability. So I think there's no simple answer for it.
Is that gonna hold as you go to, I guess, like other planets?
Well,
Not necessarily. necessarily.
Not necessarily. So for slower rotators, we tend to do longer averages because we see a little bit longer time scale variability because the planet's rotating more slowly.
Have you like come up with a rule of thumb for that at all?
I have a rule of thumb. Yes.
Well, plots like this though kind of give you a clue, right, as to how long you might want to average to capture the relevant mean state.
There's a lot of variability. This is again using 10-year averages. This is a planet that's rotating 64 Earth sidereal days in length. You can see it's fairly flat, but the reason I've run it so long, again, is because there's a lot of variability here in some of these other quantities. In particular, you see this funny. Now, this is a perfect example of something you should look out for in the model. Something's gone mad here. Look, things look so flat. This thing's receiving about 10% more insolation. G ice is very flat, so the amount of ground ice is very stable. GWTR, TR, that's the amount of water in the ground, that's also very stable. Snow DP looks fairly flat. There's some variability coming in at around 800 years, but it still looks pretty good. MWL, it looks really nice. The mouse of the water in lakes looks very clean. But you see that ZSI, the amount of land, lake or ocean ice, is going up and up and up, and it's spreading. Yeah, there's a lot of variability in it. That's bad. After 1,000 years, for this thing to keep increasing means there's something wrong here. This is an example of a run where we had a high latitude grid cell that was growing in ice. So there was some precipitation in this particular grid cell. It was a lake grid cell, and it kept getting more and more precipitation and it had nowhere to go. So the ice, there was an ice column of a couple thousand meters high in this particular grid cell. We don't have an interactive land ice model. So it just keeps growing and growing and growing.
It's like Narnia.
So you think that science fiction can come up with some funky worlds? We can come up with some funky worlds. Man, imagine walking along and suddenly there's a 2,000 meter high column of ice in your world. So that's what I'm saying. Look at these quantities. Don't just run the model along and think that everything you've looked at looks hunky-dory and I'm happy, happy, happy. Be cautious. If you're pushing the model in a regime that's really outside the normal Earth temperature bounds or whatever it is, make sure you look at these things. People with a lot of experience in this community look at these things. I'm not sure everyone looks at them because sometimes I see things in papers I'm a little suspicious of, but it's a good idea to look at as many of these quantities as possible. This wasn't too hard to spot in a sense. I mean, I saw this, but early on I had noticed that there was a grid cell when I was just looking at a normal map. There was a particular grid cell that had a lot of ice in it, and I was very suspicious that something was going on there. So we're trying to come up with a kind of a hack for this, but really we need an interactive land ice model to address this particular bug. But you can see in all the other plots, ZSI wasn't doing anything. That's because I had a lot of insulation. So it's not cold. But since this world is a zero obliquity world, and it's only getting 10% more insulation, the high latitudes are very cold, and they stay very cold. And it's very easy, because of the climate dynamics in this particular world, to get a lot of precipitation up there, snow, and if it doesn't ever get melted, because of the climate dynamics of that particular world, you get this kind of result. So I think that's a good example of cautionary tale. So these fully coupled ocean runs can take a long time to come to equilibrium. Generally, on the graded imbalance side, it's very rare that a model is not in balance within 1,000 years. Especially when I'm forcing it a lot like this. If you're using normal Earth forcings, you won't take that long. It might take a few hundred years. But the minute you start forcing the model with either more greenhouse gases or more solar insolation, the longer it will take them to equilibrium, because generally our initial conditions files are set to present-day Earth initial conditions. So your temperatures, your sea surface temperatures, your sea ocean temperatures, the column will be what they are on Earth today. So imagine there are some tricks to get around this. Let's imagine that I'm going to force the planet with another 50 or 60% solar insolation. So a trick that I have done in the past is I will regenerate my ocean initial conditions file. I'll take a grid cell from the tropics and I'll replicate that across the whole ocean. So the ocean will start out in a much warmer state, for example. And then the model will come into equilibrium more quickly because the ocean's already closer to what it should be in equilibrium than it would be if I start with the present day Earth, where the ocean's quite cool at high latitudes. So think about those things too when you're running the model. What might I change to make things, if I think it's going to take a long time to come into equilibrium, what might I change in my initial conditions file to make that really easy? Another thing you have to think about also in initial conditions, if you're in a dynamical regime that is very far from present day Earth, let's say that, for example, you're looking at one of these tidally locked worlds. It has a rotation, it has a orbital period of 11 days, and it's tidally locked. That's a very different dynamical regime, especially if you're around an M-dwarf than what Earth sees, because the solar forcings are very different, the wind speeds can be very different, and if you start out with Earth initial conditions for even the wind speeds and the temperature profiles, you can run into problems very quickly. So we have some initial condition files where the wind speeds are all zeroed out, and the temperature profile is isothermal, present day Earth. So the model starts out in a much more calm state, and it's much happier, and it'll move along and do its business. So again, when you're really pushing the model outside of the bounds of present day Earth, think a little bit about being cautious. Don't just run it blindly and expect everything to go well, because again, the model might be running, but it might not be. You might look in your PRT file after a couple days and realize, oh, the model stopped after month 1. Why did that? First month, why did that happen? And then you'll realize, oh, there's something. But anyway, these diagnostic things are super important. At the very least, you need to look at this net rad planet variable to make sure, averaging it over around 10 years for a typical Earth rotation rate is a good idea. Make sure that value is certainly within a watt. And as I say, we strive to be within plus or minus 0.2 watts on this one. We don't always succeed, but that's what we strive for.
So in the example we did today, we only did 1 times 7, but where would we find all of these monthly diagnoses?
They're in these particular ones I showed you in both of the kind of plots I showed are all in the AIJ file. So as I said, these are all extracted from every single month of these runs in the AIJ file. So
Did you make these with Canopla?
no, this is a MATLAB plot, and I can show you what that looks like. I can just, the code, it's not fancy. Maybe it's a little messy, but basically what I do is, this is probably not much.
Because I noticed in Canopla there's no option to plot it 100 times.
Yeah, you cannot generate these plots. Let me show you something that's more useful. I'll show you how I generate these.
You're using global means, we should say.
Yes, I'm using global means. What's this? Let's use. So this is just a bash script I've written that basically takes in my model run directory where all my model output is, those ACC files. You know, if I've run for 10 years, I have 120 ACC files, for example. And what this script is doing is it just basically generates the AIJ files, the very first line. This is a customized version of Scale ACC, but you don't have to care about that. So it just runs Scale ACC on every single monthly file and generates the AIJ file for those. That's the first thing it does. And then I extract the quantity of interest using NC dump. That's in your NCO tools stuff we gave you. And you can see here I'm dumping, the first line is plan ALB Hemis. That's the planetary albedo. And I dump that into a text file, the values from there, for the mean and each hemisphere values. And the next line.
Mike?
Yeah, go ahead.
I I might have missed it, but have you mentioned what the heavy variables are?
Yeah, there's three. What?
Because they want to show an NC down for,
Yes, I can. Sure. Let's do that.
show
Yeah, let's look at what one of these things looks like. So my apologies, going a little bit too fast. Let's go back to one of these ACC files. Let me just open this one again. So I can just go to. Let's go look at that file that you all have. I would always try to do that in the interest of understanding. Let's look at NC dump minus V T-surf. We like surface temperatures. Doesn't matter, it has hemispheric variables. What do you want?
Yeah, but it won't show. It will show.
Is surf underscore hemis?
Yeah, sorry.
Yeah.
Underscore hemis. And in this case, I'm just showing for the partial, but it's valid for any AIJ monthly file, okay? So what am I going to get? A lot of stuff, but the second to last line is what matters. So what you see here on the second to last line is T-surf hemis equals 14.6, 9.24, and 11.9. So the 14.6, I think, is the northern hemisphere. Or is it southern? Okay, so southern hemisphere average surface temperature, northern hemisphere average surface temperature, and the global mean surface temperature, 11.9. So that script I showed you pulls these three values out and dumps it into a text file.
So you don't have to worry about the area weighting. and all that stuff.
No.
Yeah, it's already done.
Precisely, it's all done for you. I don't want to think about it. And then basically I just pull out these three values into what I call a CSV file, comma separated variable file, and then I plot the global mean value. That's what you saw in those diagnostic
Yeah, so
tables.
this is variables that are available for every field in AAJ file.
Yes,
It's
in
not
every
average.
variable field. So I showed you about 10 different variable fields from the AJ file in those plots I showed before. So I'm pulling out all of those this way. It's cumbersome, unfortunately. You don't have to do those plots necessarily, but at the very least you should take a 10-year average and look at the net radiative balance of the model and make sure that it's reasonable value. But it's good to do those plots to make sure that everything is looking nice. Something crazy hasn't happened. The model's very complicated. There's a lot of places for it to go haywire. Like all of these models.
Yeah, and you can take 10-year averages just using
Some files.
Some files. It's basically a AAJ file. It's, you get the averages and then look at this.
Yeah, you can use some files to make a yearly average from 12 months of output, and then again look at this quantity, the net red planet value. That was the first thing I showed you, and that should be again, as we aim for plus or minus 0.2 parts per person. Anyway, so that's all this is. This script just basically goes through and generates all of these. You can see they're all underscore hemis, plan ALB hemis, GWTR, that's the amount of water in the ground, GI is the amount of ice in the ground, LWCRF at the top of the atmosphere, that's long wave cloud radiative forcing at the top of the atmosphere, that's the one I look at, MWL, mass of water in lakes. I have more here than I showed you plotting because in some instances I'm looking for other strange things. Like here you can see I have PREC underscore hemis, precipitation, global precipitation. Is it climbing? Is it doing something strange? I've seen cases where it was doing funny things. Q-surf, what's the surface humidity doing? Is it doing funny things? Q underscore 100 hemis, that's what's the specific humidity at the top layer of the atmosphere. SST hemis, sea surface temperature, global average. Is that looking okay? So all of these things are things that can be plotted once you pull them out. These are just the ones I'm interested in, but as you saw, the AIJ file has, well, I don't know, 230 variables or something. It's a lot of variables. It's a lot to think about.
More than half of them you will never be interested in.
More than half you will never be interested in.
Maybe 2/3 of them, maybe 3/4 of them you'll never be interested in.
It's true. Very true. These are the ones that I have found most interesting, at least in my explorations. Anyway.
Evaluating whether you're in equilibrium is one thing. Naturally, the science question you're trying to answer is another thing. So there may be a lot of other variables you'll be interested in for the particular science thing you want to do.
So it's almost lunchtime. Any last questions before we go? Oh, Tony's trying to show me something.
So this is a different run of the model.
But our people online
than the one
can't
that,
see it. Can
yeah,
you
they
tell me what that is? Do I
Okay.
have that?
Yeah,
Is it
I don't
one of
know.
my plots?
So that's ProxenB 04FT.
Hold on. It's
ProxenB.
Oh, I do, yeah, I'll wait on that.
this is a
Yes, ProxenB 04F underscore TL. Oh no, 04.
Sorry, wrong directory.
Okay.
I have different
Okay.
model types running in different.
Anyway, it's ProxenB 04FTL.jpg. FTL.
Okay, this is what Tony wants to show you. Oh, I don't want them to see this. Are you crazy?
Your 10-year average is not going to give you the information that you want for that run. It's apparently
orbits.
yeah. Oh, those are orbits, right? Not years. But still, this is something that seems to be fluctuating between two climate states, and if you look, over a long enough period of time, it's not going anywhere systematically, but it's every once in a while it goes crazy and dumps a lot more snow, and then comes back down and stays relatively quiet for a while, and then goes through some other period where it dumps a lot more snow and then comes back down, and but clearly it's not trending anywhere, and so to me this looks like it's something that's sort of on the edge between two different climate configurations.
Yeah.
And I actually have reason to believe that, but
This is an aquaplanet, by the way, so there's not even land stuff going on here. This is just and it's still very strange. And you can see it took a long time also for the radiation to come into balance, and that radiated.
But this is a run for where if you have any experience thinking about atmospheric dynamics, this is a run for which the Rossby radius of deformation of the atmosphere is very close to the size of the planet, and so we think it's sort of on the edge between two different dynamical regimes that have been discussed in the literature several times. And
Yeah, you can see before 2000 orbits, the rate of balance was really far out. It took a long time for this thing to get even close radiatively, and probably, there's other things going on here. There's a lot of variability. So yeah, good example. Thanks, Tony. We're showing you the secret sauce.
I just want to say, I found similar transient behavior for tidally locked planets in CAM, where it's not going anywhere, but it's flat, and there'll be a big spike, 10-degree spike in temperature for a small period of time, and then come back down. I haven't looked at snow in particular, but I found something similar for similar simulations that I didn't have a good explanation for.
yeah, and I don't know that we have a good explanation for this. It's we've looked at a whole bunch of things to try to convince ourselves that the model's not doing something stupid, but
Clever scientists can always come up with good explanations.
right.
Whether they're realistic.
Now, is this problematic if it's coming into radiative balance?
It's coming in really
So I guess you're just limited to what you can say about
Exactly, we're limited in what we can say.
so we can
What was the question? Sorry, I'm not sure if I heard it.
Sonny was saying it's a testable hypothesis, slow it down or speed it up. So we didn't do that in our simulations, and that's certainly one way to do it. And
Be more explicit, because then everybody's going to get what you're talking about. Slow down or speed up what?
the rotation of the planet, I assume Sonny is referring to. Okay.
You mean the orbital period of the planet?
No, the rotation period of the planet.
Rotational period of the planet, not the
Sidereal rotation period.
This
Okay,
is a
because
time-locked world, so.
huh?
it's the
Yeah, but
same
it's still,
thing.
but it's still,
But
it
those
still has a.
parameters are decoupled.
Yes.
Be
It's
explicit.
not just that they're decoupled in the model; it's that they matter. You have a tidally locked planet, okay, in a 6-day orbit like TRAPPIST-1 E, and in an 11-day orbit like Proxima Cen B. Okay, those are two different rotation periods for assuming they're synchronously rotating.
Thank you for
and
explaining
they're-
it that way. That's what I wanted to
Yeah, okay, and they're in different dynamical regimes, or on the edge of different dynamical regimes at least. So anyway, so one way you change the Rossby radius of deformation is by changing the rotation. So we didn't do that in these experiments, but what we do have is a set of experiments that changes the static stability of the troposphere, which is in the numerator of the Rossby radius of deformation. And yes, and so if we go off on one side, then we don't get this funky behavior.
Okay.
And it's only when it's basically when we add methane to the atmosphere and stabilize the the tropospheric lapse rate that this stuff starts to happen.
You won't
Yep.
see many plots like this in publications. People tend to leave the bodies buried where they may be.
Well, we talked about it in the paper.
We
We didn't
did
show the
talk
plot.
about
We
it.
talked about
Yeah,
it.
we didn't show it. We're equally guilty at some level. But yeah, this is an extreme example of something to be aware of. Why these plots are useful and why you should do them. If you're pushing the model in a regime that is really far from Earth, keep an eye on it. Make sure it's looking useful. Okay, I think we should go to lunch. We'll take a break. We'll be back at 2. I think that time, I think we've covered everything we really wanted to cover in terms of details of the model, so we can do some more hands-on stuff this afternoon. A lot of that will be driven by you, the consumer. We may, if time permitting and interest, sufficient interest, we may also show how we can generate phase curves and transmission curves from the model output. If I can get that together, I should do that first.
Do all programmers have us in spherical averages?
In the AIJ file, yeah.
That would save me a whole lot. I mean, I will get it starting to rate, like, oh, how can I average? I got it compiled by form. Can't find MPI, but I know I
Okay,
can.
okay, we're gonna hang up.
Sitting at this or that. Sorry.
I could also show, I say,
First period.
Definitely reminds me of like the regime change stuff that's got an episodic behavior that
Yeah, right.
all the for instance in like Venus I used to the episodic behavior that's exactly what it is. Yeah, the humps is just like the chaotic nature of the system, and you can even see where it lines up on the bottom right, like, all the way through.
Yep.
And it's just that.
Yeah, and of course your first inclination is to say, oh no, the model's doing something funky, but I think there's a very good chance the model's doing something real.
Yeah, you're just on the edge of
fundamentally